Welcome to a presentation of the HARE Privacy Aware Framework. The importance of protecting privacy rights of patient data is more crucial than ever. Conformance to regulations such as the European Union's GDPR is mandatory. However, at the same time, making healthcare data available to researchers or healthcare providers in a timely and compliant manner is key to providing better care. In this presentation, we will give you a brief overview of the privacy-aware framework being developed by the European Union HARE project, and demonstrate how it can be used in healthcare environments to implement policy-driven data privacy requirements, and consequently help the healthcare industry gain more value from their data. HARE's privacy-aware framework, built on top of IBM's Fabric open-source project, was developed to solve this. The privacy-aware framework is able to securely and transparently gather data from electronic health records in order to supply data to authorized requesters, such as for example a patient or a researcher. It enables users to define a set of privacy policies which describe who is entitled to access the data in their medical profile. Passwords to access stored medical records are securely maintained and handled automatically. Before we start discussing the privacy-aware framework in detail, let's take a brief look at FHIR, which we will be mentioning a lot. FHIR, or Fast Healthcare Interoperability Resource, is an emerging standard from the Health Level 7 standardization body. FHIR is designed around Internet communication protocols and creates a standard model for the representation and transfer of healthcare data. Currently, FHIR defines over 140 models, called resources in the healthcare environment, such as observation, patient, and consent. FHIR has been gaining rapid acceptance in the medical world. In fact, the U.S. government has made FHIR a key component of its interoperability initiatives, including the 21st Century Cures Act and the Office of the National Coordinator for Health Information Technologies Interoperability Standards. HARE's privacy-aware framework builds on and expands IBM's open-source Fabric framework. Fabric utilizes, for basic building blocks, Kubernetes and Istio for container orchestration, and adds in other open-source technologies, such as the Open Policy Agent, or OPA, for policy definition and evaluation, and Vault, for the management of secrets. Privacy-aware framework users configure human-readable YAML files to help customize their desired security solution. Let's take a look at the privacy-aware framework's conceptual architecture. Starting on the left, a user authenticates with Keycloak in order to get a cryptographic token known as JWT, which will embed user attributes like role and organization. This token will then be attached to the header of every request for data. Data requests are communicated via REST protocol, which is also the mechanism that FHIR uses. The entry point for requests into our Kubernetes system is through an ingress gateway. In fact, this is the only entry point to our Kubernetes environment and forces all data requests to go through the privacy-aware framework. The ingress gateway is able to validate the JWT on the inbound requests before forwarding them to the privacy-aware framework. All requests for data are logged to a Kafka message queue. Logged information includes metadata describing the request, such as the requester and a timestamp, as well as the policy-driven decision taken by its policy manager on how to handle the request. The blockchain module will extract this information from the Kafka queue for immutable logging. Finally, the privacy-aware framework will pass the incoming request to a backend server, which is typically a FHIR server, in order to extract the required data. Based on an evaluated policy decision, this data may be transformed before being returned to the requester. The privacy-aware framework has the ability to transform the data to be accessed by the user, removing or anonymizing sensitive data fields, based on policy and the conditions of the request, such as intent of use, the role of requester, and the requesting organization. In fact, the flexibility of the privacy-aware framework will support an unlimited number of requester parameters and policy conditions. Before returning data to a requester, the policy-aware framework enacts organization-defined access policies based on the categorization of the data being returned, such as personally identifiable information, or PII, to determine an action that needs to be carried out on the data before it can be returned to the requester or exported to another data store, such as a healthcare registry. Since FHIR precisely defines the fields in each resource, the healthcare data officer is able to categorize individual fields by assigning them labels such as PII. This will allow the privacy-aware framework to enact privacy policies at a much finer-grained level than is available today, where typically access policies are at a resource level, either a requester gets access to the whole resource or is blocked. The privacy-aware framework also provides a simple graphical interface to toggle the PII labeling of categorized fields. Let's now look at 4 use cases that we have implemented in the HARE project that highlight different applications of the privacy-aware framework in hospital environments. The first use case that will show the tremendous potential that HARE offers in allowing a patient or researcher access to a federation or linkage of data from any number of healthcare registries which may be distributed across the Internet. In our simulation, we are linking the National Diabetes Registry with the Prescription and Cardiovascular Disease Registries in order to show how a diabetes researcher will be able to correlate data records across registries. The second use case will show how we can use the privacy-aware framework in conjunction with the FHIR consent resource to restrict a researcher's access to FHIR observations according to the consent rights assigned by each patient. After this, we will examine an envisioned scenario to seamlessly export diabetes data from a FHIR server in a hospital to the Norwegian National Diabetes Registry. Finally, we will briefly discuss our use of blockchain technology for logging of data access actions and how the privacy-aware framework can provide role-based accessing of this information. We have 2 types of data requesters in our linkage of healthcare registries scenario: patients who should be given a collection of all their medical records from the linked registries, and researchers who want access to a large collection of medical records from the registries, but based on policy restrictions, can only be given information with personally identifiable information removed. We start with a patient submitting a request for all of her medical records from the linked registries. The patient's identity is authenticated by a login process, and a cryptographic certificate is generated and attached to every subsequent request. This certificate identifies the request as being of type patient information and embeds the requester's patient ID. When the privacy-aware framework receives this request, it uses securely stored passwords to go out to all the linked registries and retrieve all the records associated with this patient. All data is returned to the patient without filtering or redaction of values. Next, a researcher will issue a request for all records across the registries for a medical study. Once again, the request will be accompanied by a cryptographic certificate identifying the researcher. The privacy-aware framework will gather the medical records, and based on the data categorization we previously discussed, will replace PII fields with X's. In this example, we can see that the subject ID has been removed. Now we will see an example of how the code could be run. A patient will submit a REST command requesting all of her records. This request goes to the MyRecords endpoint. A JWT, seen in the token field, encodes that this is a patient request and specifies the patient's ID. We now see the FHIR resource information, which is returned to the patient without redaction of values. The researcher will now request all fire observations for a medical study. Similar to the previous case, a JWT will encode the requester role, which this time is researcher. Note that the REST endpoint is now all records. The privacy-aware framework will anonymize all observation information which has been classified as PII, replacing the original values with hashed values. Hashed patient ID values cannot be decrypted to reveal their original values, yet remain unique, allowing for records to be grouped by their hashed values for analysis. In the second use case, the consent management use case, we use a hospital-based fire server which is storing observations for all patients, along with the consent records for those patients who have agreed to make their medical records available within a given time period for a given purpose, such as medical research. Records which do not have an associated patient consent record will not be returned. A researcher makes a request for all medical records. Here we see part of the fire consent record from patient 009, Elliot Salant. Upon receiving a request for medical observation records, the privacy-aware framework will match the consent record to an observation for Mr. Salant, and then check to see if the exam date falls within the consent window. If so, the record will be returned to the researcher. The privacy-aware framework policy can easily be configured to anonymize PII information before it is returned to the researcher. Once again, we will look at how this could be executed through a REST command. Here the researcher is issuing a command to the fire server, in actual fire syntax, to request all observation records. Observations relating to patients who did not give explicit consent to unredacted use of their data, or fall outside of the consent time window, are redacted with X's. Records with the proper consent conditions will be returned unredacted. Our next use case shows a scenario where the privacy-aware framework could be configured to transform and then export all received diabetes data to the National Diabetes Registry. Patients monitor their glucose levels, which are then uploaded to a fire server in the hospital. At given intervals, the privacy-aware framework gathers a 2-week window of diabetes observations from each active patient in the fire server and performs a statistical analysis on the collected data. The results of this analysis are then exported in a web-presentable format to a secure, cloud-based data store, which is accessible by the National Diabetes Registry. We can see that no S3 buckets currently exist in our storage location. In the window on the left, we will start running an emulator, which will send simulated continuous fire glucose monitor observations to a fire server. We can now see the monitoring information being generated. Behind the scenes, the privacy-aware framework is grabbing the fire data in 2-week windows, performing statistical analysis on it, and sending it to the S3 store. Buckets are being to appear, where each patient is assigned their own bucket. Drilling down into a bucket will allow us to see the processed results. Note that the original fire observation data has been transformed and reformatted in a manner which will be easier to present to a researcher. For accountability purposes, the privacy-aware framework logs information about received data requests, who requested the information, when it was requested, the actions performed on the returned data, for example, anonymization, and other parameters to a blockchain ledger. Blockchain gives a cryptographic guarantee that stored data has not been tampered with. HERE's blockchain will therefore store in an immutable manner information which tracks who accessed what data over time and for what purpose, and can be used to help detect potentially malicious, unauthorized access attempts. This logged information itself can be considered as sensitive, and different roles in the hospital's environment should be given access to different parts of this database. For example, the IT administrator investigating suspicious activity might be given access to all blockchain data, whereas another role may only be allowed to get a summary of data access requests, without any details about the requester or decision taken on the request. The HERE blockchain-based auditing mechanism has built a framework to extract meaningful auditing and monitoring information from the blockchain metadata. This information is made available through REST endpoints, which can be easily queried. Here we see how we can visualize the access attempts through a Jupyter Notebook, which uses these endpoints and then plots the returned data. Thanks for your attention.